All right, so thank you very much. First of all, I'd like to thank organizers for their kind invitations, for this opportunity to give a talk. This conference, so I will talk about our recent work with Gleb Katausov about the Bethe state norms. But the main technical tool which I'm going to use for study these objects be the ODE IQFT correspondence, which is a subject, well, that is one among the subjects of this conference. I would make a comment why I prefer to use this. Usually it's called IDIM, but I would prefer to use IQFT correspondence. I will say a few words about this. And this correspondence, actually, there are many phases of these correspondences, but for me, the best, in my point of view, this correspondence can be formulated in the following way, most general, I would say. This is corresponding between a special class of solutions of certain classical equations, integrable equations, and the so-called Bethe states in quantum field theory, integrable quantum field theory. Bethe states mean the certain special basis in this among the of the stationary states, so that is as I said, that there are many phases of this correspondence, and it was already discussed on this conference. But my favorite example, I would say, like a toy example for such a correspondence, actually, it goes back to the probably mid of 80s. This reference. It's relations. It's a toy example because in the IQFT side of this relation would be not just quantum field theory, it would be a quantum mechanical problem, the particle and periodic potentials, at Mathieu equations. And since that time it was, maybe, I'm not sure that it's a first mention and first reference for this relations. But anyway, it's a relation between the states in the quantum mechanical problems. The states, it's a Floquet states characterized by periodic potential, characterized by quasi-momentum, and the certain class of solutions of the Pinlever-3 equation. So here is the Pinlever equation, certain coordinate frame, and these certain conditions. And you see that in the expansions, when you're doing the expansions of the solutions, you see the energy which appeared in the expansion of Pinlever equations. It's appeared played the roles of an energy for quantum mechanical problems. But anyway, I'm not going to discuss this example in details, and that's in fact it looks like a simple simple example for ODE IQFT correspondence, but it's actually more complicated than I'm going to discuss today, which is the simplest possible. I prefer to work with the simplest possible models I can imagine to understand the physics behind this. But the question, in principle, having such a correspondence, the question we can address the following. Okay, we know this relation. Suppose we know this correspondence between the solutions. What can we say, something useful about the quantum mechanical problem, about the quantum field theory, in particular in the language of the quantum field theory? Say, what can we say about the correlation functions? And maybe simplest correlation function can imagine. So from the point of view of the quantum mechanics, such as simplest correlation function, this matrix element, right, overlap, which is so how to calculate this? For example, how to express this in terms of the solution of Pinlever-3 equations? And I don't know the answer for this question, but I'm sure that there is some interesting simple formula. And as I said, I'm trying to explore something simpler, even this one. But I'm trying to discuss. I will discuss the model, which is actually related to this model somehow. But the model is a kind of, it's always used as a kind of experimental laboratory to develop ideas of integrability. This is so-called XXX spin chain. Perhaps it's one of the first, the original integrable model. And so this is a spin chain. So they described by the if you will start with the spin chain with the finite length L, then the Hamiltonian is given by this formula, simple formulas, and it depends on some parameter, an isotropic parameter. And the physics, actually, the physics of the model is different for different values of the parameters. In particular, when delta in between -1, the system is critical. It possesses certain scaling behaviors which describe the integrable quantum field theory in this domain. Its low energy part of the spectrum can be described in terms of quantum field theory. And that would be the subject of my interest, exactly this domain. So once the delta, the anisotropic parameter in this domain, we can conveniently parameterize by Q. It's a standard parameterizations, where Q is a Q of S. And also, I'm going to use actually the parameter beta squared. It's a kind of historical notations, and the parameter beta and from 0 to 1. It's a parameter anisotropy, right? It's a parameterize the model within this domain. Okay, and also it's important that I would I will need some additional parameters, which is k here. It's a parameters appear in the boundary conditions. We impose the quasi-periodic boundary conditions. And you see, let me from the very beginning emphasize the k-defined model to the integers, right? Because for this definition, you can add any integers to k, but it will not change these relations. I will assume that k belongs to this interval, so-called, physically speaking, it's a first Brillouin zone. And that is important. And the Hamiltonian itself, if you write the Hamiltonian in terms of k, it's a periodic function of k. That is crucial. This is very important for us, actually. All right, and as I said, this is one of the first integrable models. The quantum integrable models was actually solved by Bethe, and the famous Bethe and Zas was introduced in this work. And actually, so this is basically the idea of Bethe, what is written in transparency. So the idea is start with try to first use the fact that the Hamiltonian commute with the total spin operator as Z. So we can start with the configuration when all spins up, for example. And actually say that in some point, the spin is actually flip the spin at some point, which is labeled by x1, xm-1. And then write the search ansatz for the stationary wave functions at the superposition of plane wave. Just a standard plane, like a standard plane wave, with a certain amplitudes, AP, which each amplitude, so this is the ansatz, it's a Bethe ansatz in the original formulations, right? It's an ansatz for the wave functions, but it turned out that if you, this amplitude is just write the product of kind of two body factors, you see this function f involves only momentum of the, you can think about these particles like wave functions of the propagating the free particle magnons using the physical language. So it involves only the moment of magnons, of two magnons. It's a particle reducible problem in this sense. But anyway, so if you take this wave function, substitute to the boundary conditions, then you immediately see that that indeed wave function, if the momenta appeared here, satisfy these equations, right? And this is famous Bethe and Zas equations. And theta here, it's a ratio of two, theta is the phase. It's a exponent of the I theta. It's a ratio of two body factors. So this is the Bethe and Zas equations. And the Bethe and Zas equation depend on k, on the twist parameter k. All right, and so this is the equations, and now we have these wave functions. Everything is defined, and the equations. What is the simplest possible quantity you can ask? You can think about. So this wave function is not normalized, right? It's just written, well, it satisfies the Schrödinger equations, stationary Schrödinger equations, but it's not normalized. And the questions about, the first question you can ask at this point, what is the norm of this function? So usually the norm of the wave function is defined through the integrals of the absolute value, squared of absolute value, but here it's a variable x discrete, so we consider the sum. So that is these functions that would be the subject of our interest. And in fact, there is a remarkable formula which is proposed by Godin, McCoy, Wu in 85, how to write these functions in terms of how to, because this expression is highly inconvenient for numerical calculation, but they propose a function how to express in terms, basically in terms of determinant certain matrix. And here is the formula, and this formula was inspired original idea for Godin, and it was the proof of the full proof given by Karepin later. So that is a formula which is very effective for numerical calculation. You solve the Bethe equation, then build this matrix, and matrix M by M matrix. Remember that M is a number of roots of Bethe equation. It's related to the spin of half the total spin of operators, total spin of the state. And so that is so that formula we are going actually very convenient for numerical purposes, for calculations of norms. But we need to, I should emphasize from the very beginning that the norm itself are not, there's no canonical normalizations of the wave functions. And in particular, the Bethe equation, if you take a look on the Bethe equation, they involve ratio of the two-body factors. So actually you can multiply, it means that you can multiply the two-body factors on the functions which depends only on individual momenta, and the ratio will remain the same. So the Bethe equation doesn't fill this. So for this reason, we in order to talk about the normalization, in order to make the calculation, we should fix the two-body factors. And I'm going to use there's certain simple natural fixing conditions, way to fix it. But for this, to do this, I need to introduce certain parameterization to replace the Pj, which is a quasi-momentum of the particles, by the zj, according to this formula, and then the theta will parameterize this way. It's just a parameterizations, convenient parameterizations of, and instead of Pj we use zj. Meaning of these parameters zj will explain in the next transparency. And then we can fix the gauge by this simplest possible, perhaps it's the simplest possible choice for the two-body factors, and I will do it this way. Then that defines exactly what we need here. All right, so once you fix this gauge, once you fix this ambiguity, then the sum defined completely. So you just need to calculate this sum, for example, calculate the beta roots, and then find the sum. And in fact, so the quantities, so this is possibly example, very primitive example of correlation function, in a certain sense, right? So the quantity, which is maybe, well, and so I try to convince you that this quantity makes sense to study, right? At least. And anyway, but even for the last 30 years, it was impressive progress in the calculating many quantities in XXZ spin chain. But this object is still, we don't know any, or at least I don't know any analytical tools for study of this object. In particular, of course, we are interested in large L behavior, some kind of universal behavior, because finally, so the best we can do is make some numerical experiment, right? Just to calculate, try to extract behavior from the numerical data. And again, at this point, I should again emphasize that we will consider the states which so-called low energy, corresponding to low energy excitations. Only these states. I will return to this point. But the numerical experiment shows that this norm developed the following scaling behavior. So a certain exponent, it's typical behavior in quantum field theory. This is actually scaling behavior. It's indicated that presence that this formula can be interpreted in terms of the quantum field theory. And so the coefficient A1, A2, some coefficient which doesn't depend on state, but most interesting the critical exponent theta, and also the amplitude and infinity, this one, which is kind of a universal object. Okay, and with the modern power of computers, like there's even this laptop, it's very easy and very fast to well, you know, it's required only a negligible amount of computer time to find these quantities, all these quantities with a rather good accuracy. So you can find numerically, and then in the next step, you can, of course, the purpose of my talk is just formulate a set based on this numerical data, formulate the set of conjectures concerning these scaling quantities. All right, but before I will give this formulate these conjectures, we first need to understand what we are talking about here, because see, in this formula, it's not easy. We can find the roots of Bethe and Zat's equation for some state for given L, but actually we need to have not just the Bethe and Zat solutions for given L, but certain families of solutions. So we need to assign so we have a state, Bethe state, which is right, but we need to assign the L dependence on the state. And it usually, if you talk in general quantum systems, latest systems, it's not easy to assign this because it's just one. See, you diagonalize your Hamiltonian for the size L, for the size L prime, but how you relate the states, even the Hilbert space, even the size of the matrix are different. So there is no any natural isomorphism between these states, right? Because the dimension is different. So we should assign this dependence, but in the case of in presence of Bethe and Zat's, we can do this, but we can do this only for low energy states. And the idea is the following: how to do this process. The idea is rather straightforward. So we first take the Bethe and Zat's equations and rewrite this equation in terms. Take a logarithm of these equations and rewrite in the form, so-called logarithmic form. And of course, once you take the logarithm, there is a certain fast and ambiguity in definition of Pj. The Pj, you see, and theta j defined, it's a logarithm. It's contained, it's multivariate functions. You need to specify the branches of these functions. But once you choose it somehow, right, if you specify it, then then in the Bethe and Zat's equation, the certain set of integers, of half integers number, so-called beta numbers appeared here, right? And it's integers when the number of sides of the lattice is odd, or half integers for even. So this set of numbers, once with this given fast prescriptions for assignment for this theta and Pj, this beta number will label the states, different beta states. And the question, so you take the states, suppose how to find this beta number. So to find these beta numbers, to fix these numbers, you actually can do the following, proceed with the following. You take the Hamiltonian and diagonalize it. Just choose the some sufficiently small L, you just directly diagonalize the matrix, the Hamiltonian. But the Hamiltonian, together with the Hamiltonian, it's an integrable system, and there is a certain integrable structure, and which involve the so-called transfer matrices and the most prominent prominent role in whole integrable structures belongs to the so-called Q operators, which is discussed already today. And Q operator, and which is this operator which depend on spectral parameters, and certain spectral parameters I use the zeta, and this operator commute with the Hamiltonian. And the remarkable property of the Q operators in the case of the XSS spin chain that we can choose normalize such a way that is polynomial of order of m. M is a number of beta roots, and the roots of this polynomial zeta j exactly the parameters which is appeared in this parameterization. So zeta j's in these formulas, right? It's the roots of the Q functions, Q operators, roots of the Q eigenvalues of Q operators. So any eigenvalue has this form. So once you have roots, if you diagonalize the Q operator, so there is explicit formula of Q operator, I'm not going to use it. But if you diagonalize H and Q simultaneously, then you can extract zeta j, substitute in these equations, and find the set of beta numbers. All right? And then actually beta number depend on L, but very simple way. And once you know it for given L, you can predict what would be the value for any L. So this way you can write these equations, which is fixed equations, which is for given beta states, and each beta state would characterize this set beta numbers. So so you have equations at least. Now you need to solve it, and usually this equation of this type can be solved by iterative procedure. You need to specify the initial iterations, right? Initial approximation for the solutions. And once, in fact, if you know the solution, if you know the beta roots for this spin chain of length L, then you can use it as initial approximations and calculate and use it as a starting to iteratively solve this equation, to find it for L plus 2, for example. And this way, with this procedure, you turn on your renormalization group flow. Physically speaking, this dependence of L, the change of L, it's roughly so what physicists call the renormalization group transformation, how it depends on overall size of the systems. And once you have this, you can use these steps. You can use this as initial approximations and find that starting with the L, which is obtained starting with the roots, beta roots, for example, for given L, you can calculate for L plus 2, then for L plus 4, and so on, and calculate. So define the state for any L, and that would be works for low energy states. Actually, it's procedure. Okay, and so norm here, which I already, was written in my in the previous transparency, it's exactly the norm of these states, how these definitions. So this is highly effective procedure for numerical calculations, and then you can indeed check that behavior. Okay, but now let me say a few words about the roots of beta roots, how the beta roots looks like. Let's consider the vacuum case first, and this is a picture which shows the distribution, some typical distributions of the beta roots. In fact, the logarithm of beta roots minus 1/2 logarithm zeta j, how they distributed. And you see all the roots here are real. So logarithm, it's root zeta j positive. So logarithm are any real numbers. And the roots distributed within the segment, and the length of this segment, we see order of logarithm L. But what you see from this picture, that the most roots, or most of the beta roots, are densely distributed in the vicinity of the origin. So you see this dense distribution of the root actually very good approximated by the certain continuous functions. This is a famous relations. What happened with the density, discrete density. This is just a usual density. Approximation for the density as L goes to infinity, and you see even for this when I don't know, this L equal probably 20 or something like this, maybe more. But anyway, you see they're well approximated by the continuous functions. One of the postulates. Where is delta? Where? Delta. Beta squared equal 1, 2 or 5. Cosine 2 something. Beta squared here, and for this picture is beta squared 2 over 5. So the delta is cosine 2 pi over 5, something like this. Well, this is a pictures which is and then you see and in fact the roots which is densely distributed actually they responsible for the leading behavior of the norms. Their contribution actually, they contribute to they make a main contribution to the leading and subleading terms. In particular, you can easily show using this formula. Then the leading asymptotic behavior, which is defined by constant A2, is due to this dense distribution. Using this formula, you can easily obtain this coefficient A2. And you see that this distribution, actually these distributions, here it's shown for the vacuum state, but in fact for the lowest energy for the lowest energy states, the same happened. So the most root will be densely distributed exactly with the same density. So the difference between the vacuum states, this is ground state actually, ground state and the excited states would happen only on the edges of distribution. Here, something happened with the roots, and here. And this difference actually is responsible for universal behavior, responsible for this critical exponent eta and the amplitude and infinity. So in general, let's take a look what would be happened with the. So we actually I'm going to focus on not on this. That's not very interesting, this roots, but we are focused on this kind of roots which is in the vicinity of the edges. And in general.
How do you get A1, the coefficient?
Strictly, well, you can easily find it from numerical data, but I don't know. Maybe I'm not spent a lot of time. Probably it's not difficult to extract such a number because it does depend on state. You know that is. But anyway, so in general, the roots, of course, complex. So you cannot order it, for example, here roots, all the roots can be ordered, they're positive, zeta j positive, you can order them as natural ordering. But if in general, you can order the root in accordance, for example, with the real part. So this is a ordering prescription which can works for any states. And so this is some patterns of the Bethe roots for certain states. So you see the complex now logarithm. This is logarithm actually. This is a plane. Theta is logarithm zeta. So they're complex roots, but you still you can order them. Of course, there is roots which has the same real part, but how you order the roots with the same real part is not particularly important for us in these purposes. What's important that we are focused on the roots. If you label, if you numerate it by the index j from the left to right, then the roots at the edges possess scaling behavior in the following sense. You take the root. If you, as I said, if you keep the value j, for example, j equal 1, if you keep it fixed and send L to infinity, that roots goes to zeros. So in logarithm plane, it goes to infinity, right? Minus infinity, it goes that way. But if you multiply by the certain power of L, which is positive power of L, then you get the limit. The limit actually exists. What you can observe from the numerical data. And this is true not for the vacuum state, it's true for any states, for low energy states. So this is described the scaling behavior of the roots on the left edges, and this describes the scaling behavior through the roots from the right edges, this one. Of course, in this limit, you should keep spin as z fixed, and L goes to infinity. So that is scaling behavior, and now once you accept, well, I don't know the proof, mathematical rigorous proof of this statement, but anyway, if you accept it, then you can take a look what happened with the Bethe and Zamolodchikov equations, assuming this scaling behavior. So remember that this is our Bethe and Zamolodchikov equation, but I use this parameterization. So in these parameterizations, the Bethe and Zamolodchikov equations looks like this. And this equation holds, of course, for any L. No assumptions, any assumption. Depend on the twist k and spin as z, total spin. Now I said, but we know, now let's fix the j. Let's suppose j equal 1, 2, 3, and p, but fixed. And consider L goes to infinity, and we assume this scaling behavior, right, with the certain coefficients, L, this L. And now you can easily see when the parameter beta squared, let's make a technical assumption that beta squared less than 1/2. Then from this formula, you immediately see that the roots decay faster than the root zeta j decays faster than 1 over the L. Right? So if you take now the exponent L, then you see in the limit L goes to infinity, this turns to be 1. It's simplified, the equation simplified dramatically, and you have a 1 here, and L, of course, now infinity. So what you end up with the set of equations of these forms, and the two separate states. You see it for the left roots and for the right root, and they're separated because we sent L to infinity, right? So they're two independent set of equations. which use this capital K. This is the definitions. But in the next transparency, I'm actually going to use K itself, not exponent, but K itself. And once you take the logarithm, when you define the capital K, you should remember that actually everything is periodic function of K. So when taking logarithm, you should take to account this unambiguity, which is described by these integers, because integer W doesn't affect on the boundary conditions. The situation here is very similar to the particle and periodic potentials. All right, these integers, when the particle and periodic potentials, we have K, but in the spectrum we have a bands, right, and which is labeled by the certain integers. So in this situation, in this problem, we have a similar situations when all the spectrum is split on the bands labeled by this integer W. I call it winding number. And you can ask the question, for example, what would be the lowest energy state with a sector with the given winding numbers? And here's actually the pictures which is shown here. It shows the correspond the patterns of beta roots for the states with the winding number equal +1 or 1, and this is for W equal to -2. So this is an example of exactly the states, which is the lowest energy states in the sector with the given winding numbers. Okay, so we take this one. We now take this appearance at account appearance of these integers, and see the equations. Take again the logarithm of these equations, and then we end up with this equation like this. Two equations. We have K and K bar, and again, because the argument, the logarithm, definition of argument, it's a multivariate function. We should again fix the branches of these functions. But if you somehow fix it, then you have a set of integers which play the same roles as the beta numbers for the finite chain. In this chain we have, so any states, any low energy state would characterized by the winding number, by spin as Z, and this set of now integers. For the vacuum, for example, for the vacuum state, these integers would be just equal to J. But for any excited, for any J equal 1, 2, 3, and so on. But in general, for excited state, this is not true, and J cannot be equal to J, but they stabilized at some point. They stabilized for to the value of vacuum values. And this integer will characterize the states. So the low energy state described of the two sets of integers. And this is descriptions. This is a wide way to describe it. But this description is not particularly convenient. And there's much more convenient descriptions of the low energy state. And it's based on exactly on ODE-EM correspondence. And based on the following observations on equations of this equation already discussed yesterday by Clara, and so that is a so-called Schrödinger equation with the monster potentials. There's some story about this equation, how this appeared. But anyway, these equations, if you ignore this strange term with the logarithm, that is just anharmonic oscillators with a radial Schrödinger equation for radial part of three-dimensional harmonic oscillator. Alpha is a parameter, arbitrary parameter here. L is angular momentum, but now in this equation we consider L as arbitrary numbers. Alpha would be positive numbers. So, so without these terms, this is differential equation has two singular points. Then one of these singular point is a regular singular point at x equals 0, and another irregular singular point at x equal to infinity. But together with these points, there is additional singularities, the number of equal to n, and this is a so-called apparent singularities. They define in such a way that the wave functions remain single-valued functions in the vicinity of the singularities. It's rather rigid conditions, and it leads to the set of algebraic equations for the position of apparent singularities. And so that is a remarkable features of this equation, that it possesses so-called exact Boltzmann. Usually, you know the WKB Boltzmann-Feld quantization conditions, but for this type of potential, there exists exact quantization condition. And well, and this exact Boltzmann-Feld quantization has this form. If you take a look on this equation, then you see that exactly what we get from XXZ spin chain. And this, we see the link between the spin chain and differential equations. And, but of course, we should identify a parameter alpha related to the beta squared, anisotropy parameter, and 12 plus k. It's, remember that, what is k? K is this one, right? K bar. So this way you see, this way you see that we can characterize from this, we learned the following lesson from this exercise, then we take the states, take the limit of the beta state, normalize it such a way that the limit exists, right? This state is clearly normalized to 1, then the limit exists, and L goes to infinity. We expect that our system described the space of states, the Hilbert space, has the following structures. It's described by the states, chiral state, W bar and W. And W here, it's a collections of the apparent singularities of the corresponding monster potential. So instead of using these integers and J, we are going to parameterize our state by the apparent singularities. And since we have two independent equations, two independent Bohr-Sommerfeld quantization conditions, we need two independent set of apparent singularities, two independent set of constant potentials. Okay, and the immediate questions appeared: how many states we can build, construct such a way? And it was an original idea where we gave some argument in our work with Sasha and Volodya, that the number of such states is equal to number of partitions of integer n, and it was just recently proved by David, right? I don't know, it's not published yet, right, but at least there is some draft of this. So that is proven that this formula, this number of, so you see the number of states, would be exactly the number of states on the level on the Fock space. If you have a Fock space, you can consider the level subspaces, number of such states equal to AMG, it's a creation negation operators, and the number of states in the given level subspaces exactly equal to number of partitions. So you see that this consideration shows that the states, the scaling limit of the states, beta states, actually can be interpreted as state from this tensor product, where W here runs from integers, it's a winding number. So this would be the Hilbert space of low energy. We describe the low energy excitations. And this is exactly the formula which appeared to the standard Bazhanizations of the XXZ spin chain, and describe the low energy part of the spectrum, described by integrable quantum field theory. And this is the reason why I prefer to use integrable quantum field theory, because this correspondence works only for the universal scaling part of the spectrum. It not works for the whole the spectrum of EM. Means you can. It looks like that you can perform the same similar for let's say for finite L. That's not true. I don't know any non-trivial example on this. So that is the reason I prefer to work, because this is indeed the correspondence only with the universal part, with the quantum field theory, which is not whole story in the integrable systems usually. All right. So now I should say a few words about the norms. Now, in the spin chain, the spin Hamiltonian, just a matrix, I can use the usual Hermitian conjugations, like in transpositions and complex conjugations for the matrix. And the norms we are talking about here, it is possible to show that once you define the norm with respect to this, understand this norm and this norm, just the usual norms, just the naive matrix norm. It's possible to show that the beta state, if the twist parameter is not 0, then the beta state corresponds to different solutions of Bethe equation orthogonal. So that this naive Hermitian structure consisted with integrable structure of the actually systems, because beta states are orthogonal. So the norms here, it's just the inner product of the state with respect to this one. And the similar, well, in the space, on the Fock space, there is a natural Hermitian structures, which is defined by the simple formulas, which is positive definite norm, defined norm, and it's turned out that in the scaling limit, this norm turned to be just Heisenberg norms. So that is very natural to actually expect, and it's indeed true. And then we can, now I can formulate the conjecture, this result of numerical calculation, that the critical exponent eta here, it's really depends only the level of the state, n plus bar. So basically, so that is a very, so it depends on state, but rather simple way, right? And this is a formal, and furthermore, this amplitude factorized, okay, because it's natural from this formula, right? But anyway, so we can ask the questions. This way we get the certain basis in the Fock space. So what's special of this basis? And the answer is that this basis is consistent with certain integrable structures, which is studied in our works more than 20 years ago with, again, Volodya and Sasha. And so these states actually diagonalize the certain set of so-called local integral of motions. And the eigenvalue of this local integral of motions can coincide with a certain symmetric polynomials with respect to the apparent singularities. So that is the simplest one is the power n minus 1. So in the case I0, you have a 0 power, so you have only number of apparent singularities. Then you have a linear function, this is a sum. Then you have a quadratic one. So that is a general formulas. And well, in principle, you can at this point you can ask the questions: how I can extract? Suppose I given the set of beta numbers, I given the set of beta roots for given L. So how I identify the scaling limit, right? So what would be the natural instrument to test this? How to extract from numerical data this state W, scaling limit of this state? And actually, in this respect, this most important object in integrable structures, this KDV integrable structure, plays the so-called reflection operator. This operator was introduced by Sasha and Alyosha Zamolodchikov in context of studying the study of fluvial theory. But it's a part of the integrable hierarchy, integrable structures. Actually, its appearance can be explained the following way. We consider if you take the scaling limit of Q operators, and the scaling limit becomes it can be represented, there's explicit formula of the Q operators. It can be shown that the Q operator coincide, the eigenvalue of Q operator coincide with the spectral determinant of the Schrödinger equations with the monster potentials. As usual, okay, and you can formulate the spectral problem for these standard spectral problems, and the spectral determinant given by these formulas, and then they're all essential integrable elements of integrable structures appeared in the asymptotic expansion of the spectral determinant for large E. So this is asymptotic expansion, which is actually was discussed yesterday. For some particular case, so this was more general situations, and the coefficients in these expansions appeared, the coefficient eigenvalue of local integral of motions and dual unlocal integral of motions as whole. The most interesting object in this expansion, this is well known, but most interesting object is this one, the first subleading asymptotics in these expansions. And these coefficients can be interpreted as an eigenvalue of so-called reflection operators, these operators. And what's remarkable that reflection, you can easily extract the eigenvalue of reflection operator from the numerical data from the beta roots using these formulas. You see, if you build this, if you know the beta roots, then take this product and then rescale it proper way. This is just nothing depend on L. Then you extract the eigenvalue of that operator. So it's very easy to find this numerically and predict the value of this eigenstate. And then, from other hands, it's easy to calculate the eigenvalue of the reflection operator as an operator acting in the Fock space. And here are some formulas, examples, how this for level 0, for level 1, for level 2, there's some explicit formula. And this is just picture which shows how to principle uses to extract and identifying the scaling limit from the numerical data. So this formula actually works very well for any practical calculations. Okay, but now, I'm sorry, I already probably I should. Okay, okay, but now the last thing I should mention that the Fock space actually possesses the structure of the Virasoro algebra, representation of Virasoro algebra. And here is the formula, Bazhanization formula for the Virasoro algebra. And you can actually formulate the problem of diagonalizations of the integral of motion just intrinsically in terms of the Virasoro representation of Virasoro algebra. So that state you normalize somehow. This is normalization conditions, and then you immediately see that in Virasoro algebra the natural definition of norm. This is conjugation, the natural conjugation of Virasoro algebra, and you can calculate the norm of the state with respect to these conjugations. And this is different than the conjugation with respect to the Heisenberg algebra. There are two different norms. So it means in our calculation, when I said let's calculate the norm, the question, with respect to what norm? With respect to what Hermitian structure? There's two natural Hermitian structures. And the first Hermitian structure, the immediate questions are how to define this Hermitian structure for the lattice of the finite L, of the finite length. For the first Hermitian structure, already discussed, it's just the usual matrix conjugations. But what about the star conjugation, which becomes the conjugations for Virasoro algebra in this limit? And here are the formula. So actually, you can do this, introduce this conjugation by making the certain similarity transformation with matrix U, which depend on Q operators. And then you shows that this conjugation exactly because U is a scaling limit, actually it's a product of the right and left reflection operators. Then you can show that this conjugation, lattice conjugation, turns to the Hermitian conjugations, natural Hermitian conjugation for Virasoro algebra. And then you can ask, you can consider these combinations as the norm of the beta state with respect to these star conjugations. And now it's simpler to calculate the norms, start the calculation, numerical calculation norm using this with respect to star conjugations. And to explain, to write our conjectures, I need to introduce certain functions. This is some entire function of P. It's given by mid-close integrable representation, meets certain duality relations. And the conjecture which was extracted from the numerical data the following. So this norm of beta states actually it's just can be written in terms of this entire functions, and the norm it's just a norm calculated with respect to Virasoro algebra Hermitian structure. All right, and returning to the original problem, you can rewrite everything in terms all the conjecture in terms of the norms, but now calculated in Heisenberg algebra. So basically, this formula is the main result of this work, and that given that make definite predictions for the norms of the state. And you see the appearance of a certain function which is very natural, natural for Liouville theory and all this business we know from the quantum field theory. But anyway, so these are my conclusions. So we discussed how to track construct the elimination group flow for the beta states. So the calculations very greatly facilitated for the ODE, using the ODE IQFT correspondent, and the central role in whole business belongs to the flexion operator, which is object, which is not, well, that's usually not, people don't discuss. So we formulate a certain conjecture. This is not discussed here, actually was not discussed, but what I would also say that, of course, everything what I tell here can be generalized for the higher rank and for of course, the norms now would be the norms with respect to certain W algebras, but I think so all this can be done for this more general situation. Thank you.
Mentioned that there is, you cannot extend your framework to finite, so you need to be in the limit.
Yes, yes, the ODE correspondence.
An infinite number of
Yeah, there's some situations, right? The so-called Stroganov point when you can say something about the correspondence for finite, but it's not particular what we expect from.
So essentially, it's because you need an infinite number of.
Yeah, because the different the nature of you cannot generalize it for general situation. The general situation works that you differential equations appear describe the only universal part of this of the model, right? So for this reason, I would insist to use this integrable quantum field theory. Well, that would be great, but I don't know any example. I don't know any example, practical example. Well, except, but I don't. For my opinion, it's not. There's no need, just a particular point because of this, some special symmetries there. All right.
So I have a question. Have you tried to include the contribution by irrelevant operators?
Oh, well, for this one, you see, for the spectrum of energy, I didn't mention this, but the relevant operator appeared in the expansion of the energy, for example. You can extract, you can see the appearance of TT bar here. That's exactly. And this formula actually, its manifestation, that is what we expect from the quantum field theory, right? We call the business as TT bar business, that kind of corrections here, right? And I think it's, so that is if you ask me about the correction to these terms, right? This one, right, you find. It's interesting that you see in this picture, this line shows the dependence. This is what predicts from quantum field theory, and this is numerical data, which is left-hand side of these equations. So this is just and divided by this factor. So it tends to the certain numbers which you can extract from there. But these corrections, you see, this is exactly what you asked me. But this correction is 1 over the L. I don't know how to interpret it because it's not local. Well, I don't know what operator how you interpreted these corrections. You see that it's not 1 over the L squared. Because here we have a next term 1 over the scale squared, but this is not it doesn't look at the local contribution of local field here. Yes.
There is one particular case when alpha is equal to 1. I don't remember better.
Alpha equal to 1. It's a free fermions.
So it's case like Gaussian.
This one. It's a free fermions, which is.
When alpha is equal 1 alpha.
This is discussed today in the third talk, right? So it was but this is exactly the case with of Stroganov points. This is case correspond to delta equal minus 1/2. This is a Stroganov point, and this is a point with the additional supersymmetry. Many symmetries appear. You can actually give the. By the way, you can write the norms explicitly for any L. And one of the we checked actually that this formula actually consistent with this one. But this is a special point. It's a very special point, especially if you should set also L equals 0 here. All right? Because that's only the case. And it's not kind of. I don't know any. It would be great to find something, some system indeed where this correspondent works for the finite L. All right.